It's, I mean, I'll start off with back learning, so that's why I want to, that's how I want to start off. But then I might start doing things like, okay, learning half spaces, and more from a analysis point of view.
Okay.
And gradient descent type things, optimization.
Okay.
And then I might go on to like these newer things like tensor methods, stuff like that. And,
Okay.
Learning topic models by doing some. I mean, there are all these more recent stuff which I want to do.
Last question.
Yeah.
The homework, can I just claim that there is a linear algorithm to find all the strong inputs in the graph, or I need to show?
No, so that problem actually assumes that you have a strong connection graph.
It's not.
Oh, it's for a different reason. Oh, right, yeah, sure.
I can just claim that because since you not mentioned that, but there is.
Right. And also, I mean, 1B, I didn't ask for a specific running time. As long as it's polynomial time, it's okay.
Yeah, but
Yeah.
I mean, I can update the assumption I mentioned.
Yes. No, you can. This sort of thing you can keep because it's well known. You probably
Well, it's not that kind of, I don't think all of us.
Yeah, that's the thing, right? I mean, I don't think most people can come up with it, but still, it is.
Yeah, but if I know the algorithm, I can put the algorithm on it, but it takes too long to explain.
And I don't think
And then I just speak a line, find all of these points that I can from movements on the graph, and I say after time, the algorithm is
so that's the order for next semester. I don't have like a formal thing planned out, but that's the general outline that I want to do a little bit of learning theory and then I want to move on to some of the more basic stuff, see what is
Okay. Will you be spending any time talking about like RKHS type things?
Not that much.
Okay.
Because
They're not super-
kernels will come up.
Yeah.
I don't know. I'm not a big fan of. I think Jeff and Suresh are more of. I think they like to view everything as an RKHS and something happening there.
Yeah.
I'm not that big a fan of. That's what I'm thinking.
Okay.
This is all a.
I think it's.
philosophical thing. So.
I don't know. I think it's just like the different kind of problems.
Right. Yeah, so I want to look at problems that are more concrete and more, and try to show some kind of good generalization.
Okay.
Okay, let's start. So today we'll start something new. Okay, so we'll start off with randomized algorithms, and something many of you would have seen examples of them, but we'll try to see how you reason about randomized algorithms, how you come up with them in some sense. Okay, so just a quick recap. So last class, for those who missed it probably, we did this very important theorem called the Max-Flow-Min-Cut theorem. And as I said last time, it's one of the first tastes of this general notion called duality. And that will come up again in the class. So maybe a couple of weeks from now. Okay, so for those who missed the class, I would encourage you to go back, read the notes for maximum mechanics. It's very important here. Okay, so alright, so let's start with randomized algorithms, right? So far, all the algorithms that we've seen, so if you give it a certain input, it produces a fixed output, right? So the output that it produces is always just dependent on the input. And such algorithms are called deterministic the because the output determines the input, right? So these are called deterministic algorithms. Okay. And so what we're going to explore in the next couple of lectures is, is there something beyond deterministic algorithms? So for instance, if you allow an algorithm to make random choices, then could it actually perform better? And by performing better, we mean usually find better solutions or find solutions quicker. Okay, so find okay, so this is the theme of the questions we'll see. And let's start with a really toy example. Okay, so this is a very extremely simple example. So you have an array A. Okay, so indices go from 0 to n minus 1, and you know that the numbers 1 through n are written in some order in this array. Okay, so it could be, if n is 4, the array could be 3, 4, 1, 2, something. So it's just a permutation of the numbers from 1 to n. And what I want you to find is some index I such that a of I is even. Okay, so suppose n is even, so n is up 2 times k. So you know half the indices are odd, half the indices are even. Right? And I ask you to find some index I such that a of I is even. Okay. So what would be the most natural thing you do? Yes, so you just iterate through the numbers and you just you go from 0 to 1, 0 to n. From 0 through, if you really want, you can go up to n over 2 and you should be guaranteed to find 1. And output I such that a of I is even. Okay. But this itself is, the running time of this is O of n, right? Because you go over roughly n indices, okay? And in the worst case, this is the best you can do, right? Because, potentially if you had an input where all the odd numbers come first, and then all the even numbers come, and this algorithm really takes time, which is O of n. So, could take time n by 2. Okay. But in this case, note that if you just randomly sample some element in the array, okay, so just pick an index I at random, and you randomly pick some I, and you look at this element. So what's the probability that it's odd? Or what's the probability that it's even? It's exactly 1/2, right? So if you pick the random element, the probability that you succeed is 1/2. Okay. So the probability that a of I is even is 1/2. So just this extremely simple algorithm where you just pick some random index, test if that is a good index, actually works with probability half. Okay, so this is a very toy example, and this is the kind of places where you would obviously expect randomization to help, right? Because okay, so maybe you first sampled one element at random and you check what it is, and let's say it's even. Let's say it's even, then you're done. Okay, so if it is odd, what would you do?
Pick another random.
Yeah, pick another one at random and so on, right? So, okay, so let's say you do k trials of such an algorithm. Then you can easily convince yourself that each time the probability that you fail, that is, you don't find an even number, is half. So probability that you fail all the time is 1 over 2 to the k. Okay. And note that with k, this actually drops extremely quickly. Okay, so if you set k equals 100 or something, then 1 by 2 to the 100 is it's a really, really tiny number, right? So, and that's the probability that you fail. Okay, and you can also make this formal. Okay, so what's the expected running time? Okay, so this is something that I'm going to define now. So how would you define the expected running time of this sort of an algorithm?
This case in most cases.
Sorry?
You can do this case in most cases.
Yes, but what is the worst case in this case?
It's an over 2 selection. So
It seems like we want a confidence interval.
Yeah, so this is, I mean, this is how you normally define the expectation of a random variable. Okay. So this is an algorithm in which we have a bunch of parameters. So the first thing is you have the running time. And if you do k trials, then the running time is O of k. So let's ignore the O for now, just think of it as k. If you do k trials, the running time is O of k. And the failure probability is 1 over 2 to the k. So what the question I'm asking is, I'm considering the following algorithm, which is keep doing random trials, keep performing random trials, until you find an even index, you find a good index. So in the worst case, this algorithm could go on forever. Okay, because you could just be unlucky and you just keep going on forever. Okay, so this is the algorithm that I'm considering. Okay, every step you do a random. You toss a coin or whatever, pick a random index, and you check if that index is good. Now you could be extremely unlucky and you could just keep going on forever with never finding an odd index, right? But you have this guarantee that running time is, so you have this guarantee that probability of running time being bigger than or equal to k is at most 1 by 2 to the k. So this is what we just saw, right? Okay, so the way we analyze this sort of algorithms is you think of the running time as a random variable. Okay, so is everyone comfortable with the use of the word random variable? So yeah, I guess it's basic probability. So hopefully, if you're not comfortable with it, you will look it up. Okay, so random variables are basically you have some random process and you measure something about that process. Okay, so in this case, the measurement is basically the number of steps this algorithm takes. And for a random variable, there is this notion of an expected value, which is so this is the running time is a random variable that takes values from like 1, 2, and so on. So this is the number of steps for which this algorithm ran. And what we are saying is the probability that you are over k, so the probability in this region is at most 1 over 2 to the k. Okay. And if you do this calculation, so what is the expected running time? maybe I will write it on the next slide, even though the next slide says something else. Okay. So what is the expected running time? So the expectation of any random variable is just defined as the sum over all possible values it can take. Okay. So sum over, so in this case the values it can take are basically 1 through infinity. Right? So sum over k equals 1 through infinity. K times probability that runtime equals k. Okay. So this is how the expectation of any random variable is defined. Okay. So in this case runtime is the random variable, and you just integrate over the whole the set of values it can take of the value times the probability that it takes that value. And now in our case what we know is that this is at most 1 by 2 to the k. Okay, so that's what we just argued. Probability that you have not found until k minus 1, okay, so it's k minus 1. So if the running time is k, then it means that you have not found until k minus 1. Yeah, and I guess you also have found at k, so it's exactly 1 by 2. Alright, so you have something like this, and this you can easily evaluate. Okay, so for those of you who have seen geometric progressions, you can evaluate things like this, and this turns out to be a constant. This is actually at most 2. Okay. So the expected running time is pretty small. Okay. And you also have a further guarantee that the probability that the running time is at least k is at most 1 by 2 to the k. Okay, so you have really good bounds on what the running time is going to be. Okay. So any questions about this expected running time? Yeah.
So the numbers in the array, they're in just some arbitrary order.
Yes.
Then how is picking a random index any better than just doing a linear?
Yeah, so that's exactly what I want to do here. Okay, so that's exactly what is on this slide. Okay, so when you think of randomized algorithms, you think of the input as given beforehand. Okay, and then your algorithm makes random choices. Okay, so I think so his point is a really good one. So what he's saying is, so look at what the algorithm is doing, right? So it's examining the array indices from 1 through n in some arbitrary order, in some random order. Okay. So suppose you knew what order it was going to examine things in. Okay. So suppose I know the algorithm is first going to look at the 10th element, then the 3rd element, then the 4th element, and so on. Then I can arrange the input such that you actually take roughly n over 2 steps. Right, because I could just make the first n over 2 things bad. Okay, but so that is something we don't allow when you are designing randomized algorithms. Okay, so what we just prove is you assume that the input is in some sense oblivious to the choice of your randomness. Okay, so you have any input, but it's fixed beforehand. Okay, so the input is given to you. Then your algorithm tosses coins. Okay, then your algorithm picks random number. So that's a subtle but a very good point.
Well, but so if you pick a random index,
Yeah.
the probability that the value at that index is even or odd is 1/2, right?
Yes.
But if you just do a linear scan and pick the 0th index, the
Yeah.
probability that it's even or odd is still 1/2.
No, the 0th index is always fixed, right? So given an input, the 0th index is either even or odd. There's no probability there, right? Because the first number in the array, it is what it is, right? So if it's odd, it's odd. If it's even, it's even. So there is no probability there. I'm not saying that the array is random. Okay. The array is something that's given to you. Okay, and yeah.
So it's the same thing. Say you have there are n different permutations for each array. So over
all the set of all inputs, they're both going to have the same running time, right? It's exactly what you said. Like, if you're given an input that is arranged randomly,
Oh, okay.
then you suppose you have say n factorial inputs in factorial different arrays, and you run both algorithms over them.
Yeah.
They're both going to have the same running time.
They both, yes. So there will be some input. So once you fix the random choices that the array is making, that the algorithm is making, then there will be, some permutation for which it does badly. Okay. But the point is, the input cannot, the designer of this input does not know what the random choice of your algorithm are.
So he doesn't know the random choice, but say that he gives n different inputs, n permutations.
Oh, right. So on one of them it could take long. Okay.
No, so the algorithm in which you iterate through, and if you take all permutations of all inputs, then they both will have the same running time.
So I see. So you want to consider an algorithm where you just iterate through the indices.
And you want to consider an algorithm which makes random,
which does this, okay?
And you run them over all permutations of all inputs.
Right.
They will both have the same running time, right?
So they will both. In fact, this random thing could do very badly. It could do. On some inputs, it might actually take more than n over 2. Okay, but that's fine because that's not what we are saying. So what we are saying is, so that's why you have to be more careful when you write down the proofs of these kind of algorithms. So what we will say is, for any given input, the expected running time is at most 2 of 1. Okay, so it's at most a constant. So that's what we say. Okay, so you are given the input, and then you make your random choices. Okay, and afterwards you analyze the probability. Okay, so yeah.
So since you're making this argument, let me say that if you have n elements, you can make in fact a loop operation for this thread. Then I know that half of the time my original algorithm, the algorithm that it creates half of the time it will also have an expected running time of 1, right?
Yes. But that's not an expected running time, right? So on half the permutations, it will have a running time of 1. Yes.
So then what is the...
No, because the point is, you can, so given the algorithm, okay, so what's the previous algorithm? It's just run through the indices and come up with, run through the indices and find the first even number, right? So given this algorithm, I can easily construct an input where it's going to take n over 2 steps. Okay. Correct? Okay. Now I give you a different algorithm which says every step I pick a random number and I check if it's even or odd, and I continue until I find an even number. Okay. I give you the description of the algorithm. I just didn't tell you what the randomness is. Okay. Now for this algorithm, you can't give a fixed input which will take n over 2 steps. Because for every given input, it will actually take, only a constant numbers. Okay, so that's the point. Yeah.
Yeah, I think you said what I was going to say in so many words, that the advantage of the randomized is that if I'm the adversary supplying the input, I can't gain it, I can't engineer it to make it perform worse because
right.
of the randomness.
Yeah, so basically, you give the algorithm up front. Okay, so this is how you always think of analyzing algorithms. You always say the person the adversary who is designing the input knows the algorithm. Okay, he just doesn't know what the random choices are. Okay, and so that's the point. All right, so good. So this is good that you asked this question because I was wondering how to make this technical point. Okay. All right. Okay, so this is nice. Okay, so for certain problems you can come up with algorithms that have guarantees like this. But so randomness inherently comes with a bunch of philosophical questions. Okay, so the first question, many of these don't have answers. Okay, so the first one is, how do you generate random numbers? Okay, so on a regular computer, so most things you can think of are deterministic, right? So what's the source for random numbers? And this is like a very interesting research question. A lot of people study these things. In fact, I think random numbers today are just based on some physical quantity of a computer, like something to do with the temperature or something like this. Okay, so there's no really good answer to this. And you could say, okay, so how do you tell if some number is random, right? Because once you write it down, it's no longer random. Okay, so that's the usual issue with this. And the second thing, which is more a complexity question, is do we actually need randomness in algorithms? Okay, so does every problem essentially have an algorithm that is deterministic? So this is something which is again not known. Okay, okay, I should allow. So to formalize this question, this is not exactly the same running time, but suppose I allow a polynomial slowdown. Okay, so suppose I tell you that there is a randomized algorithm for a problem that runs in time t of n. Can I say that there is a deterministic algorithm that runs in time poly of n times t of n? Or t of poly of n, something like that. Okay, so the usual way we do in NP-complete. So this question is one of the big open questions in complexity. Okay, and we don't know the answer to this. So these are, I guess, somewhat significant philosophical questions. The other ones, which are more aesthetic questions, are basically, okay, so is it okay for an algorithm to give different outputs for the same input? Okay, so people, depending on your use case, you may or may not like it. Okay, so, but this, I think people have come to accept it, because once you get used to this idea, it's okay. And the other thing which again you have to get used to is, so most of the algorithms that we come up with, we show that they work with very good probability, right? Like in this previous example I said, in 100 steps, your algorithm will succeed with probability 1/2 to the 100. Now you could say I am not happy with that level of probability, but it is what it is, right? So most people would be happy with the probability of 1/2 to the 100. Okay? So this is again something that there's no real answer to this, so it's just depending on the problem you might want different levels of probability. Okay, so these are some questions that you've got to keep in mind when you're thinking of randomized algorithms. Okay, and so now let's see how we are going to analyze randomized algorithms. Okay, so I think we've seen many aspects of this even in the store example, but let's see. Okay, so for deterministic algorithms, we had a very simple formula, right? So first you come up with an algorithm, then you say, oh, okay, I'm going to prove its correctness. That it always outputs the right answer, and then I'm going to bound the running time. Okay, so it's a simple story, right? So now, some of the algorithms that we see may not even be correct. Okay, so they may not always be correct. Okay, so they will be correct with good probability. Okay, so the previous algorithm we saw is always correct because when it halts, it actually finds an even index. Okay, but we'll in a bit see an example where the algorithm could make mistakes, okay, but the probability that it makes a mistake is very low. Okay, so here this sort of issues also arise. And the second thing is what we just saw, which is that you only have some bound on the expected running time. Okay, or you might sometimes have stronger bounds, like in this previous example where the running time is k with probability 1/2 to the k. So you might have good probabilistic bounds on the running time. So throughout, by the way, WHP refers to with high probability. So, good to keep. Okay, so these are the main differences, and we'll illustrate both these two things. Okay, so let's do that. So I wanted to start with one of the earliest examples for randomized algorithms. Okay, so how many of you have seen this example before? Okay, so I guess some of you might have seen, but you probably not. I give you this number, let's say. So it's turns out this is a 44-digit number. Okay, and I want you to say if it's prime or not. Okay, so how would you do this, right? So how would one normally do this?
You try to divide for all numbers from 1 to 1.
Yeah, you can check all numbers from 1 to either this number or its square root or something like this. And you check if that number divides this. And testing if a number divides another number can be done quickly. Okay, so that can be done in time polynomial in the length. Okay. So this one, but it still takes time, which is something like root n, square root of 2 to the n times poly n. Right? So remember, n is the number of digits. Okay. So 2 to the n is roughly what that number is, and then you have poly n. Okay. So the question which a lot of people, I mean, it's one of the most significant questions. So now recently it's been answered. But the question is, can you find a polynomial in n-time algorithm to test if this number is a prime or not? Okay. So the interesting thing about this question is, if you can test if it's prime or not, it's like testing if it's composite or not, right? Because it's just a negation of this. And so if you're able to do it, it gives this interesting thing that you can tell whether a number is composite without actually factorizing. Okay, because people believe factorizing a number is difficult. Okay, but testing if it's composite or not is easy. Okay. So you can test whether a number can be, is factorizable. You can't find the factorization. Okay, so it's one of these few problems where we don't know how to do this. Okay, anyways, so why do people care? So there are many other reasons, but the most basic reason why people cared was that you could do a lot of things in time which was polynomial in n. Right? So you can compute, you can add, multiply 2 n-digit numbers, you can even find the GCD of 2 n-digit numbers in poly n time. Okay. So this is the only thing here which is not trivial. Okay, but Euclid did it 2000 years ago, so you can probably come up with it. Okay. So, right, so the question is, can you test primality in time like this? And so this is one of the first examples of a randomized algorithm, and this is due to Miller and Rabin. So, I guess this randomized algorithm is due to Rabin. Okay, so Miller came up with an alternate algorithm. So the question here is what we've seen. So you're given some big odd integer q. You can assume it's odd, that you can test easily. Okay. And it has n digits. Okay. And you want to find out if it's prime or not. Okay. So the key idea behind this Rabin's algorithm is, it's actually an old observation, which is that if you have an odd number, and so being prime is equivalent to saying that the only solutions to x squared equals 1 mod q are 1 and minus 1. Okay. If you don't know exactly what this means, it's fine. Okay, so if you know modular arithmetic, okay, so if you have a prime, okay, so if q is 7 or something, then the only numbers x such that x squared is congruent to 1 mod 7 are 1 and are x equals 1 and x equals 6. 6 is because 6 is like minus 1 in mod 7. Okay, because 7 minus 1 is 6, right? So 6 is like minus 1 And just the same way that if you take squares of regular numbers, right? So -1 squared is 1, 1 squared is 1. Okay, so the same sort of thing holds in modular arithmetic also, when Q is a prime. But the point is, as soon as you have Q that is not prime, okay, so you will start having solutions where x is not 1 or -1, but still x squared equals 1. Okay, so for instance, if you take 15, right? So if you take Q equals 3 times 5, this is 15, then maybe x equals 4 is the solution. Okay. So x squared will be 16, which is 1 mod 15. And this is a non-trivial solution to this equation. Okay, because 16 is x squared is 1 mod 15. So, and it turns out this is a general thing. Okay, so if you can find a non-trivial solution to x squared congruent to 1 mod q, then it's a proof that q is composite. Okay. And for every composite q, there is such a proof. Okay, for every odd composite q. So this is the main idea behind this Rabin's test. This is actually an observation that was known much before this. But what he showed is this very clean way to test, to find such an x. Okay. So what he said was, you start with a random, you start with some x in the range 0 through q minus 1, and you try to compute x to some appropriate power, and it turns out that, by trying a bunch of powers, okay, so you can try to look for a solution to this. Okay, try to look for a solution to y squared equals 1. Writing y just to so as not to confuse with x. Okay, so let's not go into what this Fermat test is. Okay, but think of it as a procedure. Okay, it takes this input. I'm calling it ft of x. So ft of x takes input 0 through q minus 1, and it succeeds if it finds a non-trivial solution to y squared equals 1. Okay, so that's when I say that this Fermat test succeeds. So what Rabin proved was that if q is prime, okay, then ft of x fails for all x. Okay. And this is true just because there is no non-trivial square root. So there is no way ft of x can find a non-trivial square root. Okay. By the way, is the phrase non-trivial square root clear? I've been using this for a while, but so what I'm saying is a non-trivial solution to y squared equals 1. Okay. So it's the square root of 1. That's what I'm saying. Okay. So yeah. Okay. So let's call it a non-trivial solution. Okay. Or a non-trivial y. So what he showed is that if q is a prime, then ft of x will never succeed. Okay, so it will fail for all x. So that is easy. But the more interesting part is if q is composite, then it succeeds for at least half of the x's in 0 through q minus 1. Okay, so let's not go into the proof of this, but this happens. Yeah.
What's the value of x? Where are we?
So so this statement says that if you look at x equals 0, x equals 1, and so on, try out all possible x's in 0 through q minus 1, says that this test will succeed for at least half the numbers if q is composite. Okay. So in some sense, this is exactly parallel to what this toy problem that you've seen, right? So what we said is, so you have the outputs of this test ft of x, right? So let's try x equals 0, x equals 1, 2, so on until q minus 1. Okay, and suppose you write down in this array Okay, so this is the output of fp of x. Okay. So imagine writing down such an array where the x element is the output of ft of x. And this is a binary output, right? So it either succeeds or it fails. Okay. And what this previous, what they showed is that if x is prime, then for all x this test fails. Okay, so this array just consists of all elements being failed. Okay, and if x is a composite number, then for at least half these things, it is actually a success. Okay, so that was what these guys showed. Okay, so if you think of this array as just being populated by success, failure, then this is the property they have. Okay. And now it's, yeah.
Does that mean that as soon as one of the x's passes the test, you know
You know that it's composite. Yes. Okay. So if in this array you can find some x for which the test is passed, then you know that the number is composite. Okay. But if a number is composite, you have something stronger. You know that for half these numbers, it actually passes this test. Okay. So this is exactly like this odd-even problem, right? Because what we are saying is if it's composite, okay, then half the numbers are passed. So I could randomly pick one of these numbers, test if it's pass or fail. If it's fail, then okay, there's nothing I can do. And I can try another random number. And suppose I do this k times. Okay, so suppose consider this algorithm to perform this test for k random x's. Okay, and turns out each of these tests can be done in poly n time. Okay, so that's the point. So each of these tests can be done polynomial in the length of this prime number. Okay. And so note that now we have this guarantee about this algorithm, right? Because if q were actually prime, so all these tests fail. Okay, so you always get fail, and then you can answer prime. Okay, so you can just say the number is prime. But if the number is composite, then you know that the probability of finding something where the test passes is at least 1 minus 2 to the minus k. Right? So this is the success probability. The probability that you fail all the time is only 1 by 2 to the k. Okay? So if you think of k equals 100, then the probability that you return a wrong answer is extremely tiny. Okay? So is this analysis clear? So the algorithm is just pick k appropriately. Okay, so k depending on how much level of satisfaction you want. Okay, so think of k being 100 or something. Then try essentially k random x's. And if one of them returns a pass, then you know that the number is composite. Then you say that the number is composite. None of them return pass, then you just say that the number is prime. So this is an example of a case where you could make a mistake, right? So the algorithm could make a mistake. So it could say that a composite number is actually prime. Okay. The probability of the mistake is only 2 to the minus k. Okay, so it's a probability of mistake is 1 by 2 to the k. So this is an algorithm where the running time is fixed. Okay, so it's only k times poly n. But the error probability, but you have some probability of making a mistake. So any questions about this?
Could you just please repeat that? It would be at least is 1 minus k, 1 minus 2 to the power minus k. What do you mean by that?
So WP is always with probability. Okay, and so what this is saying is, so when you return composite, right? So you return composite if the test passes at least once. So you return prime if the test never passes, right? So suppose Q is truly composite and the test never passes. So what is the probability of that happening? It's 1 over 2 to the k, because each time there's a half probability of failure, and the probability that you fail k times is 1 by 2. Alright. Okay, so we'll look at another example. So here, it's again, no, it's actually an old example. Okay, so we've seen how to solve this problem. So you have an array from 0 through n minus 1, you want to find its median, right? So array a0, a1 up to an minus 1, you want to find its median. And you guys have seen how to do this in linear time. But let's now see a much simpler algorithm for doing this in linear time. So the algorithm I want to consider, so it's the following. So suppose I pick a random index. Okay, so note that this is unsorted and whatever, so it's an arbitrary list of numbers, and let's say they're all integers, okay, and you want to find the kth smallest element. So I'm starting off by picking a random index I. Okay, so I picked a random index I, and what I do is I go through the array. So this is exactly what we've done before. Okay, so it is, you go through the, once you pick an index, it's exactly what we've done before. Okay, so you now go through the array, divide it into L and R, I think we call them. Okay, divide L and R such that L contains AJs such that are less than or equal to AI, and R contains AJs that are bigger than A. Assume for now all AIs are distinct, so it doesn't matter. Okay, so if you have such a thing, then so you divide the array into L and R based on this random pivot. Okay, so that's what you're doing. Then you do exactly what we did before. So if size of L is bigger than k, then try to find the kth smallest element in L and return it. Okay, otherwise, if L is smaller than k, okay, so if L is smaller than k, then find the k minus maybe plus 1. So we did this, right? So I want to be very careful about this. If k is exactly this, maybe you have to return AI and so on. Okay, so let's not go into the details. But this is the algorithm, right? So you pick some random element. Okay. You divide this array into two portions, okay, where one is smaller than AI, one is bigger than AI. And then you recurse into one of these two pieces, depending on what k is relative to the size of these elements. Okay. So this is exactly what we did last time. And when did we say that this works well? Okay, so note that this step takes time O of n, right? This step takes time O of n. It's this recursion that we needed to analyze. Right? So do you guys remember what the problematic case was? So suppose let's say I just pick the first element and divide this array. So what was the bad case? And by bad, I just mean the running time is much more than n.
It's sorted.
It's sorted in the wrong way, right? So basically, if the array that you recurse into is too big. Okay? So if you guys remember, we said that this is roughly the main issue here. So if you could find some index I such that you have each of these being strictly smaller than n, okay, so it's like 3/4 n or something like this, then you would be in good shape. Okay, so this is how the homework also proceeds. Okay. So, right, so the bad case is a very imbalanced L and R. Okay, so example could be what you just said, where L is 1 and R is n minus 1. So these sort of cases are the bad ones. But note that what's the probability of this happening, right? So if you pick a random element and you partition based on it, right? What is the likelihood that you have that you pick the smallest element in the array? It's 1 by n, because there are n elements, and what's the likelihood that you pick the smallest one? It's 1 by n, right? So this is pretty unlikely to happen. Okay, and you can try to make this formal. Okay, so let's try to do an expected analysis of what the running time of this algorithm will be. Okay, so let me formally do this. So these kind of analyses are what I call probabilistic recurrences. Okay, so it's earlier we were writing a recurrence which basically said T of n is essentially O of n. Let's forget the O and again write n plus T of max of L comma R. So this is the recurrence we had last time. And we were trying to make sure max of L comma R is like 3n over 4, something like that. But this is in general true. But this itself was just a deterministic running time bound, right? So T of n just referred to the running time of the algorithm. So now what we are going to actually do is define this expected running time. Okay, so we're going to talk about define. Maybe I want to call it something a little bit different than T of n. So let me call it S of n to be the expected running time of this algorithm. Okay. So note that this is a randomized algorithm, so you can only talk about the expected running time. Okay. So I want to develop an expression for S of n in terms of, define some kind of a recurrence relation for S of n. Okay, so how would one do that? So let's go back to the algorithm. So this is the algorithm, right? So this is called randomized selection. Let's say. So again, what's the definition of expectation? Right? So if you have any random variable, the running time of this algorithm is a random variable. Right? So basically, depending on the choice of this index, it will vary. So, okay. And as I said before, the expected value of a random variable is basically you integrate over all possible choices of the value times the probability. Okay, so that's what we saw before. For any random variable x, the expected value is basically integral over all possible values x can take of that value times the probability that it takes that value. Okay, so that's the expected value. So in this case you can write down, right? So in this case, so what is S of n? So there's always a fixed cost for this algorithm, which is the cost it takes to do these steps, right? So you've got to divide based on what I is. Okay, so that fixed cost is always there. So fixed cost is always n. And now you have this, what is the expected value of this recursive step? Okay, so that's what we're asking. Okay, so it's fixed cost plus the expected value of this recursive step. So let me write it like that, expected cost of recursive step. Okay. Alright, so okay. So now what does this mean, right? So now the recursive step, based on the choice of I, it could take n different things, right? So you could either break the problem into L being 1 and R equals n minus 1, or L being 2 and R equals n minus 2, and so on, right? So these are all the possible partitions that could happen, okay? And what's the likelihood of each of these choices? Every choice is equally likely, and there are n choices. So this is 1 by n. Maybe it's 1 by n minus 1, but never mind. Okay, so this is, each one is likely to happen with probability 1 by n. Now, suppose I have this choice. Okay. So what's the time it takes? What's the expected amount of time you have when you go into this step? It's not quite n minus 2, it's s of n minus 2, because you recurse on an array of size n minus 2. Okay, so the expected running time in that case would be s of n minus 2, right? That's by definition. So if you were in this case, then the running time, the expected running time subsequently will be s of n minus 2. Okay. And similarly, if you are in this case, I mean, let's say you are in L equals n by 2, R equals n by 2, then the expected running time would be s of n over 2. In general, it will be the s of the maximum of L and R, okay, because you could go into the bigger subset. Even if L is n minus 1, R equals 1, then it's s of n minus 1, right? So it's s of max of this. So this is fine. Okay, so what you get is n plus sum over I equals 1 through n minus 1 of 1 by n minus 1 times s of max of L comma. Okay. So does everyone understand why this max came up? It's just because if your partition has n minus 1 R, then you could recurse on the bigger piece, right? So this is an upper bound actually. So this is the bound we have, and so this is so from here, so I can write this down more clearly. So I could write this as n plus 1 over n minus 1 times, or maybe I write 2 by n minus 1 sum over I equals 1 through n by 2 of s of n minus I. Okay. So this is some basic arithmetic. Okay, so basically what I'm saying is after n over 2, it's basically R that matters, and before that it's L that matters, right? So this is what I wrote down, and now you can show by induction. So this is just a recurrence, right? So now you have s of n is less than or equal to n plus this thing, okay? And this is now you can use all the skills you've built up with solving recursion. Yeah.
How would we deal with the divide by 0 when I equals 1?
Oh yeah, so I equals 1 is never handled using this, right? So this is all, I'm writing this for I bigger than 1. Sorry, for n bigger than 1. Because you would never recurse. Yeah, you would never recurse if n is 1. Okay, so, so this is the bound we have. And this is the bound we have. And so this is the bound we have. And 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 -1, you just return whatever element. Okay. So anyways, so now you have this, now you have a regular recurrence, S of n smaller than or equal to n plus this. So it's just that the term that you're arguing about is an expected quantity. Okay, so that's why these kind of recurrences are just called probabilistic recurrences. And this you can easily solve to say that S of n is less than or equal to some 10 times n, something like that. So this is a simple exercise for you guys. I'm sure you guys can prove this. Okay, so you just assume by induction that S of n is smaller than 10n, and if you plug this in, basically there will be n over 2 terms over there, and it will cancel out, everything will work out. Okay, so let's not get into that. Okay, so any questions on how this recurrence was developed? So basically, we use the definition of expectation to say that with probability 1 by n you are in this case, with probability 1 by n you are in this case, and so on. Okay, so that's what we use to write down this recurrence. Okay, 1 by n, let me write it correctly then, because I wrote n minus 1 there, it's n minus 1 there also. And that's how we analyze. Thing we will do often. Okay, so we will have a randomized algorithm and we'll come up with a recurrence for the expected running time, something like this. Okay, so this raises a natural question, right? So you know that the running time for this algorithm is small. Okay, so the expected running time is 10n. Okay, so but is it true that but what we want usually is something stronger, right? So what we want is, okay, it's not just that the expected running time is small, you want the you want it to be small with high probability, right? So remember previously we said the success probability is like 1 over 2 to the 100, right? So it's like, it was extremely high success probability. Yeah. And now what you have is just that the expected time is O of n. So this is a common thing that happens with random variables, right? So the expectation could be very good, but whenever you run it, maybe sometimes it takes small, sometimes it takes large values, right? So how do we get around this? Okay. So is this issue clear? So what I'm saying is the running time is a random variable. Okay, let's call this r, and you know that expected value of r is small. So this is, let's say it's 10n. So what we really like to be able to say is, with good probability, I am not much bigger than, let's say, 50n. Okay, because I am willing to give some factor up. So I will say that, is the point clear? So I want to say that with probability at least, I don't know, 9/10, the running time is less than or equal to, I don't know, 40n, something like this. So I don't want to lose too much of a factor relative to this, but I want some statement of this kind. Okay? Yeah. And this sort of a thing, you could have bad examples, right? So just if you just had a bound on the expectation, so maybe you take value which is very close to 0. Okay, so maybe the running time is really close to 0 with probability half, and maybe it's really big with some probability. Okay, so and maybe you were unlucky and you were taking extremely long time. We want to say that these sort of things cannot happen. Okay, so the goal is, you want to say, so the goal here, we want to upper bound the probability that we are unlucky. And unlucky just means, let's say the running time is more than 100n. Okay, so that could be our tolerance level, right? So n could be big, so maybe 100n we can afford. Beyond that we can't afford, okay, in terms of running time. And we are asking, what is the probability that we are unlucky? Okay, probability that this means r is bigger than. Okay. So how would you prove such a thing? I mean, can you bound such a thing rather? That's the question. Okay. So suppose you had a bound that the expected value is 10n. Can you bound the probability that that r is actually bigger than 100n? So does it ring a bell to anyone? Okay, so maybe if you have not seen this. So this sort of a thing, it turns out to be quite generally true. Okay, so this is what is called Markov's inequality. So what this says informally is that if you have any non-negative random variable, okay, so if you have any non-negative random variable, in this case r, so the non-negativity is important, but for running times it's trivial, right? So it's always non-negative. Then it's unlikely to be much larger than the expectation. Okay, so formally, so formally what Markov's inequality says is, so probability that r is bigger than some t times the expected value of r is less than or equal to 1 over t. Okay, so think of t as some constant bigger than 1. Okay, so t bigger than 1 is a constant. Because otherwise probability less than 1 by t doesn't make too much sense. Okay, so we have, so this is the formal statement of this result. Okay, so it says that r is always non-negative. Then probability that it's more than, let's say, 100 times the expectation is smaller than 1 by 100. Okay, so it's pretty unlikely that you are far out from its expectation. Okay, so if you think of the real line, okay, so you have 0 out here, the expected value is here. So what we are asking is, what is the likelihood that you are more than t times the expectation? Okay, we are saying this probability is at most 1 by t. And do you guys see the proof of this? I mean, how is it, I mean, what could be the probability that of this whole region, right? So that's what you're asking. Okay, so I'm looking at the region where this is t times e of r or more. I'm asking what is the probability that you are on that side. Okay. And suppose this probability is p. Okay. Can you guys see? Yeah, because p is in the top one. Okay, so p is the probability that you are at t times e of r or to the right. And the theorem is claiming that p is smaller than 1 by t. Right? So okay, so let's see. Okay, so what could p be? So you could say that, let's go back to the definition of the expectation. Right? So the expectation basically says, the definition is e of r is defined to be integral over all the values. So small r equals, let's say, 0 through infinity, okay, of small r times p of r. Right? So probability that it's equal to r. Okay, so just to avoid confusion, let's, instead of calling that p, let's call this q. Okay, so q is the probability. It's the total probability on that side. So now note that, okay, so this is just an integral from 0 through infinity, right? So this is like saying I go from 0 through infinity, I go from 0 and move to the right towards infinity. And at every step, there will be some probability that you are here. Okay, so there will be some probability that you are at this r, at this small r. I'm just doing r times p of r. Yeah, and I'm doing this integral from 0 to infinity. So in particular, this thing is bigger than or equal to t times e of r times this q. Okay. Why is this? So I'm claiming that this integral is at least the t times e of r times q. Okay, so it's actually a very easy to see. So why is this? Because this integral is actually, I mean, you can think of it as going, this is actually going from 0 to infinity, right? And in particular, this includes the interval t times e of r through infinity. Okay? So if you call this number some z or something, then this includes the interval 0 to infinity. Okay? And 0 to infinity, the probabilities, the p of r's add up to q. Okay? So that's what we are saying. And this coefficient is always at least z, right? Because it's z through infinity, so it only increases. Okay? So this number is bigger than this z times q. Okay? And just think about it if you didn't follow it. It's actually very simple. And what this means is that q is smaller than or equal to 1 by t, because this e of r cancels out. And this is what's called Markov's integral. So it's very simple, but it's very useful. So once you have a bound on the expected value of the running time, then you get reasonable bounds on reasonable probabilistic bounds on how big the running time could be. So often you would want much better than this. Okay, so we'll see how to do that in one of the homeworks. Okay, so you can actually get better bounds than this by doing a very simple trick. Okay, so you could say run it up to a certain time. If it doesn't work, then okay, restart from scratch, and you can do something. Okay, so it's very simple. So we'll see that also in a homework. All right, but is this Markov's inequality clear? So this, remember the informal statement. Okay, so next time somebody tells you a random variable is bounded in expectation, you should know that can't be too high. Okay, so it could be low actually, with pretty good probability, but it can't be too high. Okay, so that also you will see in the homework. That be low pretty often. All right. So before I end, I want to say two things. Okay, so one thing is I've already said this, but I want to explicitly mention this. Okay, so in the first example, in this primarily testing example, the running time was always fixed. Okay, so it was always k times some polynomial in the number of bits. But it could return the wrong answer with some certain probability. Right? So the probability was 2 to the minus k. So such algorithms are called Monte Carlo algorithms. Okay, so these are just based on I don't know if there's a real reason for these things. Okay, but so these kind of algorithms are called Monte Carlo algorithms. They could fail, okay, but they always have a fixed bound on the running time. Okay, and the second kind of algorithm that we saw is this median finding, or even the first algorithm, where the running time depends on the randomness, okay, but you always output a correct answer. Okay. So that's so such algorithms are called Las Vegas algorithms. Okay. And you can easily see you can go between the two. It's not it's roughly the same thing. But for some problems, it might be more natural to come up, or you might always want to be correct. Okay, so that could be like a strong requirement for certain problems. So given, I think given the Las Vegas algorithm, you can always come up with a Monte Carlo, but probably not vice versa. Because if you make a mistake, you make a mistake. Right? Alright, so this is something to keep in mind. So another example which I won't go into, but it just follows from the previous sort of analysis. So if you guys wanted to brush up this analysis of the median, then you should do this. Okay, so so this is the example of quicksort. Okay, so here you have an array, and you want to sort it, right? So you have some array. Quicksort basically says pick a random index I again, and now you break up this array into L and R. Okay. The goal is to sort, right? So you break up into things less than I, things bigger than I, okay, and then you stick I in between. Then you sort this and this recursively, and this is the array that you output. Okay, so sorted L followed by I followed by sorted R. Okay. And you can try to analyze. You can try to define the same kind of thing as we did before. Okay, so define S of n to be the expected running time. So in this case, you will find that depending on this partition, so if you partition based on L and R, then the running time is S of L plus S of R, right? So it's not max of S of L, S of R like it was before. Okay, so now it's S of L plus S of R. And you can write down a recurrence just like before. And you'll be able to show that that is actually O of n log. So this is a very simple n log n algorithm for sorting. So this is in fact what people often do in practice because it's really easy to do. Okay, so alright, so let's maybe stop here. And next time we'll see some better, some different examples.